This video will cover the Mercuric ion-catalyzed hydration of alkynes. Just like other additions to alkynes, the mechanism of this process will be similar to the mechanism for the addition of water to alkenes using a mercury catalyst. Remember that with the alkene process, the first step was the addition of the mercury catalyst to form the mercuric intermediate, followed by reduction with sodium borohydride to produce the Markovnikov product. Hydration of alkynes works in a similar fashion. Instead of mercury acetate, however, we use mercury sulfate. Additionally, the reaction requires a strong acid catalyst. Just like with addition to alkenes, we see Markovnikov addition to the alkyne. This produces an intermediate called an enol, because it contains both an alkene and an alcohol. This enol is the Markovnikov product from the addition of water to the alkyne. However, this enol is unstable and quickly rearranges to form a ketone. This rearrangement occurs in the presence of protons, strong acid, and it is an equilibrium that favors the ketone form over the enol. Therefore, the product of hydration of an alkyne is a ketone. In order to understand why we get Markovnikov addition, as well as why the rearrangement occurs, we need to look at the mechanisms for these two processes. First, let's look at the mechanism for the formation of the enol. The active catalyst for this process is the mercury 2+ ion. In the first step of the mechanism, the alkyne attacks the mercury ion. This forms a mercury alkene intermediate. Notice a few things about the structure of this intermediate. First, the mercury adds to the less substituted carbon of the alkyne, leaving the carbocation at the more substituted carbon. This is because more substituted carbocations are more stable because of the inductive effect. Another thing to note is that it doesn't form a cyclic intermediate, which is what occurs in the first step of the alkene addition. This is probably because the alkene that is formed upon addition of the mercury ion to the alkyne would not be able to form a cyclic intermediate because that intermediate would be too strained. Once this mercury carbocation intermediate is formed, water attacks the carbocation. In the next step, water deprotonates to form the alcohol of the enol. Next, the strong acid in solution protonates the alkene. The carbocation that is formed can be resonance stabilized. Mercury then leaves to form the enol. This step of the mechanism can be drawn from either resonance contributor. In the carbocation, mercury leaves, donating its bonding electrons to form the alkene. For the structure on the right, the same thing occurs, causing the alkene to form, as well as the pi bond to go back onto the oxygen as a lone pair. Finally, let's now look at the conversion from the enol to the ketone. Just like before, the first step of this mechanism is the attack of the pi bond of the alkene onto the proton. Protonation of the alkene forms a carbocation. The proton adds to the less substituted carbon, leaving the carbocation at the more substituted carbon because this is the more stable structure. Just like before, this carbocation has a resonance structure. Deprotonation of this resonance structure by another molecule of water gives us the ketone. This process is common enough that it has been given a name. It's called an acid-catalyzed keto-enol tautomerism. Typically, the ketone is called the keto form of this tautomer, which is where the name comes from. A tautomer is a constitutional isomer that readily interconverts. Typically, this interconversion occurs through proton transfer. This equilibrium favors the ketone form because it's more stable, which is why the product of hydration of an alkyne gives us the ketone.